Designing, manufacturing, installing, and maintaining the high-speed electronic computer, the largest and most complex computers ever built.
Hello, everyone. Welcome to the Building Better Systems podcast, where we chat with people in industry and academia that work on hard problems around building safer and more reliable software and hardware. My name is Joey Dodds.
And I'm Spot Morina.
Spot and I work at Galois, a research and development lab that focuses on high-assurance systems development and broadly hard problems in computer science.
Today, we're chatting with Iain Whiteside, who is a principal scientist and the director of assurance at 5AI, a company that builds software development platforms for self-driving systems, as well as software components that others can use in their autonomous vehicles. Iain's background is in formal verification and system safety, and he spends a lot of his time working on how to build safer autonomous vehicles. In this two-part episode, we talk about some of the challenges and some of the more novel solutions that make it a bit easier to make these systems safer. In part one, we talk about how Iain and his team formalize and check the different actions and situations that a car finds itself in while on the road. Iain discusses how they're leveraging signal temporal logic and domain-specific languages to reason about the rules of the road. These tools make it easier to develop building blocks that reason about the world abstractly from the point of view of an autonomous vehicle. So it's a very interesting conversation. This sort of planning is fully dependent on sensor data, of course, but processing sensor data can be notoriously unpredictable. So in part two, we get into what it takes to make sure that the neural networks used in building models of the world are as accurate as possible and how you might mitigate issues when they aren't. So make sure to check part two as well. Let's get into it.
Thanks for joining us, Iain.
No problem. Glad to be here.
So your day-to-day work is on autonomous vehicles and in particular making sure that they're safe. Can you at a high level describe what that work involves?
Yeah, sure, no problem. So I guess we all know that autonomous vehicles are super cool and are going to, revolutionize the world. And we all know that actually people have been talking about them being just around the corner for quite a few years now. And one of the sort of main reasons for that is because building autonomous vehicles is a hard challenge, right? There's a lot of complexity in the world, but an arguably harder challenge is to actually demonstrate and be confident yourself that the system is going to be safe and safe to go on the roads. And generally what we mean by, showing an autonomous vehicle is safe is actually trying to compare it to human levels of driving performance. And generally, because these are machines, there's a little bit of a desire for them to be better than humans. So the sort of challenge of the field that I work in is how can you demonstrate that an autonomous vehicle is as safe as we know humans are? Because humans are actually pretty good at driving. My wife would say something different, but anyway. So it's worth taking a step back to the early days of autonomous vehicle testing, when it seemed like the best thing to do was get these cars out on the road with a human behind the steering wheel, just in case something went wrong, and see where the problems lie. And that's super good for systems that are getting, relatively mature and are capable of driving around the streets of Mountain View or relatively placid cities. And the challenge is that if you do some sort of statistics 101 on how many miles you would have to drive of these vehicles with a human behind the wheel or whatever, without seeing any dangerous incidents to be confident that they're going to be safer than humans, you end up with like mind-boggling numbers, like tens of billions of miles. And the reason for that is because humans are actually really good. In the UK, I think it's every 10 million miles, there's actually a crash, and it's less frequent for a fatality. I think it's a little bit less than that in the US, but that means that to get, sort of confidence of, 2 nines or 3 nines, you have to, multiply that number of miles. So basically, we've got this problem that in order to make autonomous vehicles economically viable, we have to find other ways of testing them other than just driving them on the roads. And so enter simulation, which is the sort of the clear answer. Build a massive data center, a lot of cloud computing, and run your autonomous vehicle system in virtual worlds, Grand Theft Auto style. Hundreds of miles a second or whatever speed you want to be able to do it. And then you can make a mile of autonomous driving an extremely risky mile, because you can set up all sorts of crazy decisions from humans for that. And this is a really powerful approach, actually, because it gives you control over testing your requirements, which is, as a formal verification person, you'll know that is a good thing to have requirements.
So basically part of your job sounds like is how do we make these simulation environments in a way that they're as close to the real world as possible, so when we test things there, they translate into the real world. How do you do that in a way that actually is as close to a one-to-one comparison? Because it feels like you try things in simulation and then everybody has a plan until they get punched in the face, sort of thing with reality.
Yeah, exactly. That's a real challenge. That's one of the biggest of them. So you can run a test in simulation, and your vehicle doesn't crash, or your vehicle does crash, and you need to know if in a similar situation in the real world your vehicle would still not crash or still crash. And furthermore, like if it crashes, you have to know if it was acceptable to crash or if that situation was just so unlikely to happen in the real world. Because this is sort of one of the sort of, I don't want to call it a dirty secret, but let me call it that for something pithy to say. Like, in the safety industry, we accept risk. So you're saying that there is a chance that bad things can happen, but I think that risk is acceptably low. And in the real world, when you drive and your system fails, that failure is a relevant failure and you need to fix it because it happened in the real world. But if you generate it in simulation, you don't necessarily know that it's a relevant failure because that particular combination of vehicles and sunlight or something like that was not likely to happen in the real world. Or even, there's no way that even a superhuman, like the best Formula One driver in the world, could have avoided that collision. And so you have to start building models of what an acceptable failure is, and you have to build models of, we call it saliency of a scenario, so how likely it is to happen. And then you have this whole other challenge of, well, in simulation, you have to decide whether or not you want to generate photorealistic scenes that your neural networks that are basically at the other end of all those cameras and lidars in an autonomous vehicle, if those neural networks are going to react in the same way to your synthetically generated scene. And that's a hard problem in the deep learning community called the domain adaptation problem, because from personal experience, neural networks are quite fragile too. They're input distributions.
Yeah.
Yes, I know.
Taking this approach is feels like a very healthy approach, not just for autonomous vehicles, but for software in general, right? The understanding that things are going to go wrong, and then that things are going to go wrong, basically, and then trying to work within that framework is probably better than saying, well, we're just not going to make mistakes, right? Because if you go out the door and say, like, we're not going to make mistakes, like, this week our programmers aren't going to introduce any bugs, then you're not going to be ready for that inevitability, right? And so I think it feels like in a way, autonomous vehicles, having to exist in the real world has forced that perspective on you. But I guess even for the sort of non-real, the machine-only applications, this feels like a really valuable way to develop systems, is with the understanding that things might fail, and thinking about how do we recover, how do we minimize harm in that case.
Yeah, exactly. And this type of safety approach has been used in NASA and other places for a long time. Like there are lots of interesting acronyms like ASARP, which stands for as safe as reasonably practicable, and MTLOS, which stands for minimum tolerable level of safety, which is saying, and the combination of both of those is the system safety approach that NASA takes, which says, okay, like there's a minimal level of safety that I would like my system to have. It needs to achieve this particular like level of residual risk, and I'm going to make every effort to make the system as safe as practicable. But there are other constraints in which I'm operating. So, like, I cannot make a system reduce its level of availability for safety. So, the safest autonomous car will never leave a parking space, and within the point of view of cost and the sort of economic benefits. So there are, of course, like challenging sacrifices that you have to make to come to like a safety like argument for whether or not the system is ready for deployment and whether or not the community can accept it. And autonomous vehicles, like you say, is basically the scariest use of incredibly complex cyber physical systems. Actually, it's worth talking about the structure of an autonomous vehicle. How a lot of them work. They basically split into three components. One is called like sensing or perception, which is basically a bunch of cameras, bunch of lidars, which is very cool spinning radar type thing, and traditional radars, and a few other sensors that take the world and generate an internal representation of that world. And it's generally, a list of 3D objects plus a map where things are, what speed they're going, what their heading is, and where they are with respect to the road. And so that's the sensing component. And then there's the planning component, which, based on that representation of the world and where the car wants to go, comes up with a high-level trajectory or a goal to get there. And then there's the act part, which is the lower level actuation, which is much more classical, which sort of takes that trajectory and turns it into realizable, basically acceleration, steering wheel angle, to get you where you want to go. And obviously the challenges in the first two. And the sort of, it doesn't take you long working in the autonomous vehicle space to realize that, the sensing component, the perception side, is always going to be inaccurate. It's never, you're never going to get it perfectly. And so the planning side has to find a way to plan a trajectory safely around this inaccuracies. And this is where you start to get a little bit of attention. And it's worth thinking about this in terms of a human driver, right? So like, I go out driving all the time and I make mistakes about how far a car away is from me or what our relative speeds are. And implicitly, if I'm not sure and I just seen a vehicle, I'll be like keeping a little bit further away until I'm clear, and then I can sort of like approach it a bit more. And we're sort of making all of these judgments of how inaccurate our perception is without even realizing it. And once you've got sort of neural networks involved, you need to have a better idea. And so you have this sort of compensation on the planning side for the weaknesses of the perception system, but at the same time, you can't compensate for everything. So you have to make the perception system as good as possible. And the traditional way of doing this, by the way, in systems where you have such an interface, is by having requirements. So it's a contract. So System A provides a contract that System B takes. And this is actually a really neat approach for autonomous vehicles. So you can say, well, for vehicles that are less than 20 meters in front of me on the road, I may make an error of, up to 1 meter on how far away that vehicle is. And once it starts raining, that error might get up to, 10 meters. And so the planning side can decide to drive a little bit further away and, even drive much slower when it's raining to reduce, the risk of something bad happening due to this larger error.
So basically what you're saying here is that the systems have to be, to some extent, aware of their own chance of failure, and to be able to quantify. Well, quantification of that seems critically important. But again, the specifications can't be like, we'll just always see the right thing. They have to be, we might see the right thing, but within this tolerance of what reality is, basically. And that's the kind of thing that you're trying to hold these systems to.
Yeah, exactly. And so to me, you get two big challenges in autonomous vehicles. One is then saying, is the behavior of the planning system going to be safe with respect to the sort of errors in which it operates under? So, can I safely follow a vehicle and merge onto a highway in rain with that sort of perception testing? And you have to actually be quite clear about what safe is. So it's actually, the highway code in UK is quite ambiguous in certain places, and purposefully so, I would argue, and in quite a few places contradictory to what traffic does in general. So, for example, the highway code says things like don't stop for any vehicles, and everybody, of course, stops for emergency vehicles all the time, and pulls to the side of the road and negotiates.
Speak for yourself.
Quite well. and of course, it says do not use your horn or flash your lights or use that for communication. And everybody in the UK, you won't be familiar with this in the US, but in the UK, roads are actually quite narrow and windy rather than have 6 lanes. So one of the situations you get into a lot is that there may be parked cars at the side of the road, which means you have to negotiate with a car oncoming in order to go into its lane to cross. And the way people do this in the UK is by flashing your lights to say, hey, come on, I'll wait on you. And of course, that's, technically not allowed in the highway code. And so anyway, so you have to figure out how can I actually give a non-contradictory definition of what safe behavior for my system is under the assumption that I've got a good enough representation of the world. And so That's one of the big challenges. And then the other problem is demonstrating and being confident that your planning or that your perception system, can actually meet this contract that the planner is operating under. Like, are you always only going to have 1 meter errors in the depth of a vehicle? That is how far away it is. Or is that just because that's all you've seen so far in your data? And so that is a huge problem, basically.
Okay. So then part of planning, so let's assume that the sensing is right, and we can get into sensing later. Part of the planning sounds like it has a bunch of challenges that are actually interesting there for you. How do you make sure that the planning is actually done in a way that's reasonable and safe?
Yeah, so the approach that we've been working on is trying to formalize some of the properties of what a safe maneuver is, and how you can sort of demonstrate what a system should do in practice. So let me give you an example of what type of things that an autonomous vehicle should do in certain situations, and then I can try and sort of talk about how we actually start to express this formally and also test it. So the background, of course, to this should be that we are doing, hundreds of thousands of simulations of different road traffic situations, all various types of them, and you need to have some sort of pass-fail criteria for each of them. And that's actually quite ambiguous, right? Because in various situations, there's more than one way in which you can safely negotiate a challenge, and there's a little bit of wiggle room. So it's not like a traditional like software unit test where it's very clear what the resulting answer should be. And so we started to build like a framework that actually allows you to test whether or not you're achieving safe behaviors based on your own formal rules of the road. And so, one of the types of scenarios that you tend to get in highway situations is you're driving along happily at, say, 70 miles an hour on the highway, and there's a car in front of you in one of the other lanes, and they cut into your lane because they're attempting to get to the exit or something like that. But they're driving slower than you. And so when they cut into the lane in front of you, you have what's called a sort of positive time to collision, which is, if both vehicles were going to maintain the same speed, there would be a collision in, X seconds. And a bad time to collision is, for a human, is something like 2 seconds, because it takes us quite a while to react. And at higher speeds, these things become more dangerous. And so what you would like to have is, and this is something that you can't control. So the autonomous vehicle can't go around driving assuming every vehicle is going to cut in front of it, and so never drive faster than any other car. And so the standard way in which like vehicles are expected to react safely is that, once somebody starts that movement from their lane to your lane and you've detected them driving slower than you, you've got some reaction time in which you need to start braking and start getting closer to their speed, and therefore have that time to collision starting to disappear, or until you've opened up a safe following distance to that vehicle. And so that's actually quite a complicated property to express. And especially if you're just writing it in words and requirements and having software engineers attempt to implement it, especially when the implementation might be, also, a sort of like AI-based system, or being a really complex optimization style like planner.
How do you do it?
So what we do is, we basically taken temporal logics that have been used for quite a long time to express properties of systems. And in particular, we're using a logic called signal temporal logic, which is an extension of something like LTL that allows you to express properties in real valued signals. That's the history is, essentially from electronic systems where you get signals. And it also allows you to have, bounded operators that are talking about things in terms of, they're talking about seconds, right? So you can say, eventually, with a sort of bound of in up to 3 seconds, some sort of property holds. And so, that's how you get your sort of liveness properties. And so we can, for that particular property that I was talking about, you can use something like the until operator in temporal logic that says, if a certain condition holds, that implies that you are braking until property B holds, which is the situation is now safe. And you can even use these bounds to say that you've got 0.5 of a second to actually react and start braking, and by being bounded, you have to have increased that gap so that it's safe within 3 seconds or something like that. And you can even enforce that that's a function of the speed. And so what we built at Five, the company I work at, is quite a sophisticated tool for evaluating these complex temporal logic constraints, and also a language for writing them in a little bit more human-friendly way. So you can take these low-level predicates and properties. So, for example, what is the velocity of the vehicle? What is the velocity of the other vehicle in the scene? And what is the distance to a lane marking? So we provide these, atomic predicates that can then be built into complex temporal logic constraints. And you can say something like, if a vehicle cuts into your lane, then you should react in this particular way. And, we use this to, basically express extremely complex properties for autonomous vehicles. And the benefit of using signal temporal logic is that it has this magic quantitative semantics that, instead of just saying true or false, I've broken the rule or I've not broken the rule, it actually gives you a signal out which says how safe I am or how close I am to breaking it. So it's like the truthiness or the falsiness of that given property.
It sounds like on one end, you want presumably people that don't or never will precisely understand signal temporal logic to be able to write down some specifications using, like, saying things like, when a car enters my lane, which obviously signal temporal logic by default does not provide. So you have to build something up there. You will then want to interpret that in a very formal framework with sort of written down semantics, and then apply that presumably both to the simulations that you're running, and then also when cars are on the road, you want to be able to apply it in both of those situations. Is that kind of the end-to-end view, and check whether those things that people wrote at a high level are actually happening or not?
Yeah. Okay. So there's a few interesting things there. So let me make sure that I get back to talking about stuff in the real world. But
okay.
so ever since my PhD, I've been a little bit of a domain-specific language nerd. So I've been super interested in writing DSLs and their semantics, and so this actually felt to me to be like the perfect opportunity to build a neat like DSL and like IDE on top of it. And so, yeah, what we've done is a few things. So in particular, we built a language that allows you to, quite easily like build named expressions and functions and even lambdas. It's kind of higher order actually. That allows you to build up like libraries of temporal logic properties. And so like as a tool, as a sort of commercially available tool, like our libraries come with, properties like has there been a lane change, which are parameterized according to like some various definitions. So the lane change property, which is, has a vehicle change lane starting at this time step and finishing at that time step, takes parameters like at what initial lateral velocity, so at what sort of turning of the steering wheel, for want of a better word, like, do you want to actually consider the lane change to happen, or do you want to actually only consider it starting once you touch the lane marking, or do you want some other? So we offer a lot of different definitions for that people can compose together. But at some point, you do still need to have a little bit of an understanding of the semantics of the underlying temporal logic, and that is actually quite challenging because temporal logic, and especially ours, because it also supports past temporal operators like since and historically, which can be more intuitive to write things, but they boggle the brain when you're composing them with future temporal logic operators. So we've had to write a lot of documentation to help people understand how to build these things.
And this is something that actually, when we talked to Rod Chapman, this is something that like kind of clicked into place for me. Is I've been interested in DSLs for a long time, but more from the language side. And when in the past, when I heard DSL, I was like, oh, great, I get to design a language with a bunch of features. But I think, and I think you just sort of explained this as well, it's the domain part that is super helpful in making these things usable. And I like the fact that you can pack in information about what it means to be on the road into your language is what makes it really unique. And then the language stuff has to be done, but it sort of stays under the hood. Like if you've done your job right there as a language designer, nobody knows about how hard the signal temporal logic semantics are, right? Like it works and it does the thing that you said, right? Like I said, I want to know when a car changed lanes, or I said I want to know when my car is going to change lanes, and that happens faithfully. So that means you did your work right there. But hopefully nobody ever has to. Nobody has to know how hard that composition is. Basically.
Yeah, exactly. And this reminds me of Of course, my PhD was in like interactive theorem proving formal methods. So like I always think of analogies in that space. Like, you know, in interactive theorem proving, you obviously start with low level axioms and you start building, you know, layers of representation on top of it. Where if you've done that right, you don't actually have to refer to the lower level axioms at all. Most of the time you can talk about it at higher level concepts. And so you end up, you know, you're proving theorems about, like calculus or whatever, without having to refer to anything underneath that. That's a really good thing. And like, I don't think we're entirely there yet. We haven't sort of like completed the theory space, as it were, but it's a good ambition. And, you know, the other thing that's really cool is that, you know, this is an integrated development environment. So, you know, I get to write little checks that says, oh, by the way, do you really mean to use this, because it doesn't like match from a typing perspective, and so I can do a little bit of type theory to help people. Yeah, so it's a cool approach.
So this is a product that 5AI aims to make available to people working on autonomous vehicles in general.
Yeah, so as a company, we're building a platform for simulation-based verification and validation, and one of the sort of key features that we have of it is this language and this language package, and actually an incredibly efficient framework for evaluating these temporal logic constraints. That maybe I shouldn't talk too much about like nerdy caching or anything like that, but we sort of have a really neat technique that means that you can do super fast recomputation if you want to change your temporal logic constraint, because we always save, think about it as, you know, a massive abstract syntax tree. So any time you get a pattern match in the syntax tree in any expression, we cache that and we don't recompute it. So that's kind of cool.
Sounds like this sort of tool set comes also with you said libraries. I'm assuming there's other scenarios and situations that happen that you can then build on top of if you're using these tools. Is that right? Real quick. Mm-hmm. Okay. So
yeah, exactly.
So how do you make sure those are right? Like, you know, when I say then if this happens, then do a lane change, you've made sure that that's what that is.
Yeah, exactly. So this is the real world validation side of things. So in some very few cases, we're lucky because other people have done some work for us. So in mostly Europe and a few other places in the world, there's some UN regulations that car manufacturers must obey for what a safe lane change is, and that talks about basically, like, if you change lane, you must not force any other vehicle to decelerate at a given rate for a given amount of time after a given reaction time, etc., etc. So these have been already tested and determined to be safe according to that regulation. And, you know, if you follow the regulations, everything's great. And we can relatively easily encode that. But the much broader challenge is that you have to have a way to evaluate these same rules when you're driving in the real world, either as a human or evaluating other vehicles. And, you know, one of the cool things that we do is, you know, anytime our autonomous vehicle goes out and drives in the road, we collect a lot of data that includes, you know, seeing other vehicles changing lanes beside us or in front of us or something. And we can evaluate these very same rules on a different vehicle that's not our own system and say, are you following the rules? And you probably will not be surprised to learn that quite a lot of the time, human drivers don't follow the same stringent safety requirements as an autonomous vehicle would follow. Yeah, so what we're essentially trying to build is mechanisms that can actually evaluate whether or not that rule was triggered in a situation that a human believed it to be triggered in, or whether or not any of the preconditions of a given rule failed, but the conclusion still occurred. And so it's tricky, and we don't really have anything like all the answers right now because it's a big data challenge primarily, but we're very aware of this challenge, as are quite a lot of the sort of regulatory bodies across the world and governments trying to figure out exactly how to formalize their requirements for safe behavior. So I'm hoping that through like a lot of collaboration between like all of the stakeholders, plus enough data to validate our rules, that at some point we'll get to a point where it feels like you could write a digital highway code in signal temporal logic and be pretty happy with that as being representative of what should be safe behavior. But there's definitely a few potholes along the way.
Potholes.
Right. And so that, I mean, it's yes. So it's an interesting challenge. And in the long run, what you're hoping for is like, well, obviously, like, people aren't going to follow the rules, right? I think we pretty well established that at this point. Like, it doesn't. Well, we can talk about enforcement separately and like how those things get approached, but the reality is, I guess autonomous vehicles are going to be on the road with people, and people, intentionally or unintentionally, are going to consistently break the traffic rules. And so, I guess I'm curious, in some sense, why this matters. Basically, like, we can have a traffic code. It might influence reality, but at the end of the day, an autonomous vehicle still has to do its best, even when other people are, even when other, in particular, non-autonomous vehicles, because maybe there's a world where all the autonomous vehicles eventually follow the rules. They still need to try to keep people safe. So how do these worlds sort of, is this a long-term vision, or is there a short-term value in doing this as well?
Yeah, I mean, in a world where all vehicles are connected and autonomous, it's relatively straightforward to prove that there will never be a crash, assuming there are no humans involved, like pedestrians or anything like that. I've read at least one paper that gives a proof of that. But yeah, so there's sort of two things to do with this. So one of the reasons in which we're keen to see what other drivers do with respect to these formal rules is that it helps us actually validate some of the driver models you use in simulation. So in simulation, when you're testing these vehicles, you have a car doing a cut-in, and you simulate all sorts of different cut-ins. And if you have enough data of what types of cut-ins humans do, then you can weight your distribution so you can sort of focus your simulation in the right areas and be confident that it looks the same. And that the example I always use in this case is like the sort of weird like interaction between two different drivers who are trying to understand each other's intentions. So if you're driving along a road, and there's a car edging out of a minor junction in front of you, that car is trying to figure out, can I go there? And the car approaching the junction is trying to figure out, is that car going to go? And so as a result, that driver might slow down, which makes the decision of the other vehicle a little bit easier, and vice versa. And these are quite nuanced sort of back and forth communication that happens with human drivers, and it's quite difficult to actually encode that and get that to come out in simulation. And so you might be simulating all sorts of variations of cars pulling out of a junction, but if your model doesn't allow for these types of hesitant situations where a car is gradually pulling out and stopping, you might just be missing a little bit of part of the search space by like lack of model fidelity. And so that's sort of one of the reasons why we try to make use of not just failures of our autonomous vehicle in the real world and that amount of data, but we actually try to, I sort of squeeze as much juice out of that real world data as possible by using it to validate models of other vehicles that you use in simulation.
And I guess in the long run, the pessimistic side of me says like all cars are never going to be in communication, or if they are, then they're never going to be honest about it. So it's something like having traffic rules is like in the long run might be the protocol by which vehicles are able to communicate. Is like, well, we can get you in trouble if you do this, so like you can't do that. Like just setting boundaries on, we experience it with humans. Like there's game theory happening out on the road every day where some people are getting to work quite a bit faster because they're willing to take risks that others aren't. And so, yeah, they'll swerve between lanes and take advantage of the more cautious drivers. And that, it seems plausible that world could be where autonomous vehicles end up as well. Cause like, yeah, I like to get to work fast, so I'm going to buy the car that pushes things farther is like a somewhat dystopian view of the future, but one that's maybe not that hard to imagine. So doing this code stuff early, like getting the laws encoded in a way that we can know what cars are supposed to be doing, I guess from that point of view is immensely valuable, because then we can, then we can sort of draw limits on how unsafe cars are going forward as well.
Yeah, and I think, of course, this will like open up the can of worms about like ethics in driving for autonomous vehicles, and like even is it like ethical to be breaking the rules in this particular situation because all other vehicles are, and then like that, yeah, there's dragons in there, but I think it's going to be a while before we start to get into these types of situations. Yeah. Like the thing you're going to find, first of all, of course, is humans who are, for want of a better word, trolling autonomous vehicles, right? So, in the streets of London, the first autonomous vehicle that, drives very slowly through a crowded street is going to obviously get pedestrians walking out in front of it just to make it stop. And then we're going to have to cope with that. And we're going to have to cope with, cyclists taking advantage of them in various ways.
Are you programming in a little arm that raises a middle finger on the window?
A specific number of fingers.
Yeah, fair enough. A specific number of fingers is better than this.
Well, there's different countries have different number of and configurations of fingers, I think, that are meaningful. So we don't want to.
Fair enough.
We don't want to overemphasize our American perspective.
I think people in Britain are pretty familiar with the middle finger.
Yeah, we're sort of multilingual, as it were. We can communicate in very many different ways.
I mean, I guess any number of upward raised fingers can probably be read as an insult, right? Especially if it's like the back of your hand. It's just like it just reads as aggressive.
Yeah, I mean, this is all the big level 4 or the big companies doing level 4 autonomous driving. Level 4 being the sort of big daddy with no humans behind the steering wheel. Like their main challenge is internationalization, so being able to go to other cities and give obscene gestures to people.
Yeah, right. You don't want to accidentally encourage people to cut you off by using the wrong hand gesture. Thumbs up maybe is good in some places and not so good in others.
Hey, speaking of like when you have to break the rules, this is the signal temporal logic sounds like a great way to encode some of the stuff, the stuff that you should do. But you have a property that explains what it means to do a lane change, one what does it mean to do a safe one, and one to never cross lane boundaries. At the same time, when I'm on the highway and there's something going on where I can't avoid a crash, I swerve to the side of the road where technically you aren't supposed to do that. Or I haven't been in this situation, but I imagine that if I'm about to hit a very small car with my SUV and I can instead choose to hit a bigger truck, I'm going to hit the truck.
Yeah.
all of these, especially the lane change, let's take that as a more simple one. Are you thinking, or are we not there yet in terms of how do you program those in?
Yeah, and let me add another layer of complexity. Like, generally you want to drive comfortably, and so most of the time, actually, you also have rules written in signal temporal logic again that say, don't accelerate greater than 3 meters per second squared, or decelerate with that laterally, longitudinally different values. And of course, if you have to do an emergency stop, you break that rule. And so this does get quite complicated because, as you say, you have a rule that says don't leave your lane, but actually, if you're doing a lane change, you need to leave your lane, and so you would technically break that rule. And so the way we approach this is a combination of building assumptions and conditions into certain rules. So don't leave your lane unless you're performing a lane change. Don't leave your lane unless there is a sort of the sort of way we express it is in terms of really dangerous time to collisions, and there's not enough time to brake, and you've got space to change lanes. So there's you end up building quite complicated properties. And the thing, like, I do actually have this concern that when you end up with a world that is so very complex, that you'll start having properties that are that have so many assumptions or conditions on them that you might end up getting some contradictions and missing particular spaces. And to be honest, we haven't got to a world that is so complicated as that right now. We spent a lot of time modeling safety in the highway for driving highways and changing lanes and merging. And so you can quite easily also, in the same logic, express what it means to be a reasonable lane change. So one of the properties that we can express is, well, don't change lane unnecessarily. And you can give your own, and this is sort of like, I don't know, maybe it's like a liveness style property that you've got. So it's like talking about making progress. So, one of the other rules that we have is make sure you're driving at a reasonable speed for that particular highway based on the conditions. And that's slightly different from like the standard safety properties that you get. And so we've got a couple of mechanisms. One is these conditions, and then the other is in the DSL itself, we have categories of different rules. So we can like express rules which are more on comfort, and rules which are more normative to do with following the highway code, and some which are safety, and various other types of categories.
Oh, so so basically the comfort thing, you downgrade it to like, hey, this is a nice to have, but if when push comes to shove, you can ignore it.
Yeah. So we basically by introducing these categories and hierarchies, you can basically provide enough data so that any downstream analysis can make the decisions that it wants to. And the standard model that we have in our workflow is, it's a bad thing if you break a comfort rule when you're nowhere near breaking a safety rule. Mm-hmm. And we can do this because of this neat property that I mentioned earlier and meant to come back to about temporal logic, in that it talks about truthiness and falsiness by having a signal about how close to a failure you are. Because there, instead of just black and white, you can, so for a rule that says don't collide with any other vehicles, that rule is actually the signal that comes out of that rule is basically how far away from any other vehicle, or how far away from the closest vehicle to you are you. So it's not actually saying I've collided, it's saying I am intersecting with that vehicle because I'm so close. And you can obviously put like a little, like a sort of halo around it to make sure that your collision is actually getting too close.
Is it just how far I am, or is it also how different our speeds are if I'm going towards a a vehicle or something like that? Or is it just distance?
This particular rule is using distance. The flexibility that we have in the platform is, we have other rules which say don't let me say it correctly, don't be responsible for a very low time to collision with another vehicle. So if a car is coming up behind you with a very high speed differential, they're almost certainly going to crash into you, and
Right.
the distance will catch that. But there's also a way of looking at it in terms of time to collision. But one of the properties is if we are coming up against another vehicle that we haven't seen at a high time to collision, there's another rule that will pick that up. So we try to keep rules at the right level of abstraction. We actually take advantage of this like signal nature of the logic in a few different ways, because you can actually, so in what we were just talking about, you can actually use it to say that, if we're actually relatively close to another vehicle and the no collision rule is close to passing, then maybe you want to stop caring about the comfort rule. That's sort of how we can use it. But the other way we use it is to allow you to direct the search space of your scenarios. Is there a cat or something? There we go. My dog is locked safely upstairs, otherwise she would be on my lap, getting in the way. So one of the things that we use with this signal nature is we use it to actually direct the search. So, for example, in simulation, you have parameters. You have what we call a scenario, which is basically an abstract definition of a traffic situation, and they have parameters. So you can basically describe abstractly a vehicle will start driving X meters in front of you, Y meters per second slower than you, and when it's Z meters in front of you, it will cut in at, I ran out of letters, like A meters per second lateral velocity. And so you've got basically 4 parameters which are controlling, to some extent, the seriousness of this cut-in behavior, right? So a high velocity delta between you is going to mean that when it's cutting in, it's getting really close to you, and a high lateral velocity means it's going to happen quickly, so it's harder to spot. And so scenarios get more complicated than that. But, for example, if we have rules evaluating how close you got to collision in a scenario, we can actually do something like, the easiest way to think about it is like gradient descent for like neural network training, where if you make small changes to the parameters, you can find which parameter change leads to the largest change in the safety rule, which gets you closest to failure, and you can sort of search in that direction to find failures. And this is super useful actually, because one of the big problems is that the search space for scenarios in simulation is huge, right? You've got many different parameters that are impacting a traffic situation, and you have potential and not just say potential, actual non-linearity in these systems, because the perception system might do something weird, or the planning system. So you can't just say that because I was safe between 5 meters per second and 6 meters, I'll be safe at 5.5, because something could go wrong there.
So this conversation is really actually reminding me of the conversation we had with Dan Guido, and one of the big things that came up there was, and he was talking about like what the blockchain what blockchain developers are doing, right, basically. And one of the main things that came out was the idea that testability is absolutely critical. And what I'm hearing from you is sort of the same thing. Like, you're able to develop these incredibly complicated logics and chains of rules and priorities, in part because you can go to simulation and see if those things make sense. And you can do it over and over, and presumably you can get feedback on like, well, we put this new rule in and it never triggered. Like you can get that kind of feedback really quick, or we put this rule in and it was resulting in crashes all the time. And like it's incredibly empowering to like be able to get such quick feedback about whether, and it's probabilistic feedback, right? Like no one's being like, yes, that's good, no, that's bad, but you can get a sense of like, is this broadly working for our system? And that seems like it's part of what's enabled you to build such a complicated but useful system at the end of the day.
Yeah, being able to efficiently and accurately explore the huge search space of driving in the real world in simulation is like the key challenge. And like basically everything we're doing and everything I work on now in research is to find ways to search that space more efficiently and get more information out of it. That's for sure.
So it sounds like signal temporal logic in general is very useful to express these kind of more complicated rules. I'm thinking about subject area experts, and I'm wondering how you're bringing in that input. So there's the codes and then there's the rules, but I'm naively thinking there's people whose area is driving, or the road and the rules of the road. I don't know who they are. I don't know what that job is, but I'm curious about how you think about bringing that input into, especially how you design those libraries that then get in the hands of people building autonomous cars.
Yeah. So interestingly, at Five, we work.
We're
with
all
forensic
truck drivers.
I mean, interestingly, there's so many people who have backgrounds in Formula One and all sorts of like driving spaces, and a lot with like advanced driving qualifications. And I'm kind of embarrassed when I'm in conversations with these people because they know so much more than me about this. But we also actually like work with people whose job is, I'll try and get the title right. It's like a forensic crash investigation specialist. So these are people whose job is to, analyze a crash and understand what the contributing factors were and where blame might lie and so on. And they are incredibly useful for giving you very clear and precise understandings of what right of way might be or what a sort of safe behavior in a given situation could be. And the challenge, of course, is I'm not going to subject these people necessarily to temporal logic. That's they made a different career choice. So you have to find a way to sort of help get these subject matter experts like views formalized. And one of the things you can do is once you formalize it, you can the good thing about formalizing things is that actually we have a good understanding of the boundaries of these situations with respect to some of the parameters in the equations. So we can actually generate synthetic data based on the models that can help validate that the decision boundaries are correct, if you see what I mean. So we know exactly for certain, it's like counterexample checking or something like that, like the equivalent that you can like give people confidence that the decision boundaries are right. And we find that in fact we tweak them sometimes as a result of getting that. These people have a lot of knowledge.
Thanks for tuning in for the first conversation of this 2-part episode. Please find a link to part 2 in the description.